Welcome to the examples video for electric fields. Today I'm going to show you 3 examples, and I encourage you to try it out first. If you have not already done them, go check the video description to see what questions they are. Go find the past year question and try it out. Also, in case you didn't know, for paper 4, roughly you want to spend about 1.2 minutes per mark, which means if the whole question is 8 marks, you have to kind of spend roughly 9-10 minutes-ish per that question. So keep this in mind as a guideline as you're preparing to do this under exam conditions. But I guess for the first times, it's fine if you just do it. Okay, so first one is MJ10 P41. What's meant by the potential energy of a body? This is a throwback to AS. Potential energy, they haven't asked that in a while. Usually they would say electric potential, but this is just potential in general. So sure, let's give it a general general definition. So in general, potential energy is stored, but it is most importantly the energy stored or the ability to do work. It's not doing work yet, but it has the ability, it's stored, to do work. Why? As a result of the position of the object. Are you near? Are you far? Where are you positioned in the field? Are you in the potential well? Are you on a high potential area? Yep, so that's what it means, position of an object. Wow, 2 marks. Okay, since it's just talking about general potential energy, it's fine if we say ability to do work as a result of the position of the object. Could be positive work, could be negative work, we don't really care. Okay, next. This is where we come to an interesting one. It looks kind of like momentum, collision. Does this look familiar to you? So you have 2 deuterium nuclei, 2-1, kinetic energy. They are very far apart. When you see these terms, large distance, ring some bells. Large distance means potential energy is pretty much 0. Okay, assume it's like infinity. So electric potential is kind of 0 or negligible. But then they come closer together with some kinetic energy. Okay, and that's shown in the picture here. Final to initial. So initially, number 1, they are really far away, all kinetic, no potential pretty much. And then finally they come to meet, just about touching. How do we know that? This is an important clue. Their final position of just touching means they didn't slam into each other. They didn't, like, they made it. They came to each other and just touch. That's it. And then they stop moving. At rest. That's very important. At rest means no more speed for both of them, which means both of them should not have any kinetic energy. So all the kinetic has become potential. Ooh, we will use that later. Okay. So the first one is, for the 2 nuclei approaching each other, calculate the total change in gravitational potential energy. When you see this, you want to think of, how do we calculate GPE again? GPE, I don't even put GPE now, just UG is fine. Okay, so GPE would be negative GMM over R. Negative just means it's attractive. They will love to come together. Okay, they won't have repulsive forces or anything like that. So if you want to find the change in U, there are a few ways you can do this. You could just ignore the negative sign and just go with it, but it's good practice to know how to write the negative signs in your minusing and plusing stuff. So here we want to say which one has higher GPE. It helps if you sometimes imagine the curve. Okay, imagine this is the gravitational potential energy. Just U. When they're very far apart, is there any attraction between them? Not exactly. So when they come closer, then they roll into this very negative potential well as they come closer together. So yeah, basically getting closer and closer. So you start off down there, then you end up somewhere down there. So it's much more negative, larger attraction between them, larger negative. Negative means smaller gravitational potential energy. So final, they are really close to each other. So you can write there, G, what's the mass of these things? Did they give it to us? GMM, we kind of know the M. They are both having the same mass because they're the same nuclei. But the mass of one of these guys is actually, if you see this 2-1, it basically means there's 2 things stuck together. One is a proton, one is a neutron, and that's called deuterium. So what is the mass of this thing? We can say the mass of one of these guys is 3 atomic mass units, which is U. What is 3U? Well, you kind of have to go and look at the constants and data formula to figure out what is U. Anyway, this one also the same deuterium, so this is the one mass is also 3U. Wait, did I say 3U? Sorry about that. 2U. Two things stuck together, a proton, a neutron. Okay, 2U. So let's go and multiply that down there. So GMM, so this will be 2U times 2U over, how far are they at the end? Well, this will be the separation distance. So at the end, they're really close to each other if you consider the center of the sphere. So something like this. Okay. And this is the final state. What about the initial one? Initially, they are really far apart, so it's kind of just zero potential, gravitational potential energy. They don't attract. So we get this in the end, you would have a value of, oh, I forgot to mention, what is U? Let's write it down. U will be 1.66 times 10 to the negative 27 kg. Very long to write. That's why we say U lah. 1U, 2U, 3U. Okay. So if you calculate this thing, you should get a number of roughly 1.934 times 10 to the negative 49 joules. Negative lah. Okay, what the negative tells you is just as a decrease. So this sign tells you there's a decrease, but you don't really care if it's decrease or increase. See, decrease. You see the graph on the top right. You start off pretty high, close to zero. Well, at zero, you decrease all the way down to a potential well. But we don't really care, so it doesn't matter if you write negative or not. So I'm just going to write 1.9. How many SF should I use? I could do 2, I could do 3. Because the values that they gave me are in 2SF, 3SF. Sure. I'll do 1.93 times 10, negative 49. Okay. 3 marks here. The first mark comes from you knowing this equation. Either you wrote it out explicitly or you implied it. You plugged in the correct values. Make sure you know your constants, G and U. And lastly, you do the correct calculation, then that's your final A1 mark. So, yeah. FYI, this is a decrease in GPE. Next, electric potential energy. There's more space to write it up there. But let's think about this. At first, they're very far away. Do they affect each other? Not exactly, they're a bit far. But then when they come closer, are they going to repel or are they going to attract? What's the charge of these things? Remember I draw the, what you call this, deuterium nucleus? Nuclei. So it means a proton and a neutron, which means they have a charge of 1e. That's a charge of this particle, so it's positive 1e. E is another constant. The other one also charge of 1e. Oh, interesting. Okay, so final, initial, they are both repulsive. So if they come really close, they're going to be like struggling. They're like, oh man, we don't want to be here. So if you draw the graph of electric potential, it will look something like this. This is UE, I guess you could call it that. You sort of really far off. They don't really care about each other. But then you come really close. You're doing a lot of work. You have to bring them to a very high potential because they really don't want to be together. They're repelling each other. So let's write it out. How should we, what's the first step? Oh yes, you need to remember what is electric potential energy. So electric potential energy can be calculated by K, Q1, Q2. Sometimes they write Q and Q, over R. Separation distance. So K is going to be 1 over 4 pi E naught. More constants. Okay, never mind. Don't worry about it. But let's write out the change in electric potential energy. So final state is when they are really close together like this. Right, so let's just throw it in there. Plug in all the values and see what we get for this. So K will be 1 over 4 pi. What is E naught? 8.85 times 10 negative 12. Make sure you know how to find this value in the data and formula sheet or in your calculator. But I recommend you use the data formula sheet. Get used to it in the exam. Okay, that's 1 over 4 pi E naught. QQ. Okay, let's do QQ. The charge of both of them is the same, right? 1E and 1E. So just put 1E times 1E. I'm lazy to write out the whole thing. But FYI, E is 1.6 times 10 to the negative 19 coulombs. Memorize that or find it in the formula sheet. Separation distance, right. They end up pretty close to each other. 3.8 times 10 negative 15. So let's write that down. 3.8 times 10 negative 15. This is the final electric potential energy because they're really close together. They're all ready to fly away. So that's what they are. The initial one is 0 because imagine R is very, very big. So I'll just write a note. As R approaches infinity, Q is kind of near 0. Pretty much somewhere there. Negligible, we say. So that will give us a value, if you press the calculator correctly, 6.058 times 10 to the negative 14. But your final answer, you could round it off to 2 or 3 SF. Should I use 2 or 3 SF? My values are kind of 3 SF, 2 SF. So, okay lah, 3 SF, 6.06 times 10 to the negative 14 joules. This is a 3 marks question, so check how much you got out of this. If you wrote the equation or show that you knew this was the equation, give yourself a C1 mark, compensatory mark. If you plugged in the correct values, you get another C1 mark for knowing how to plug in constants. And the last one, you got your final answer, that's an A1 mark. Okay. Use your answers in 1 to show that the initial kinetic energy is 0.19 MeV. Answer in 1. What's the answers in 1? Oh, so they talk about this part, GPE, and EPE. How are we going to show the initial kinetic energy is that? The nice thing is they gave us a value. We just need to figure out how to get that. So if you go back to the diagram, or think about the energy conversion that is happening here. At first, they have kinetic energy. Eventually, they stop moving. So the total kinetic energy of both particles should be 0. Okay. Why is it 0? Because it has been converted to GPE and EPE. So this is like energy conservation from AS all over again, but now with new things. So let's write down the energy conversion step by step. I mean, you don't have to write so much, but I'm doing this so that you can understand what's happening here. So what's happening is you have a loss in what you call the kinetic energy. So it's a decrease in change in 2ek. So 2ek. You're saying, why is there 2ek? Okay. We have the first particle, which has a loss. A second particle also lost. Each of them have their own kinetic energy. So that's gone, because they both stopped moving. But then in the end, what did they gain? Both of them kind of gain, well, these potential energies already consider both charges. So we can have that a gain in elastic potential energy and a gain in, what did I say potential? They're both potential energies. Except that one is GPE, gravitational potential energy, and the other one is EPE. So this is what's happening here. They both stop moving, but they both gain EPE and GPE for both. So how to calculate that? So you want to find initial kinetic energy of each nucleus. So one nucleus. So this will be 2ek. I'm just going to ignore the delta signs for now. How much did you gain in EPE? What was the value here? 6.06. Okay, so we write that 6.06 times 10 to the negative 14. That's how much we gain in electric potential energy. If I say elastic, smack myself. Okay, how about gravitational potential energy? Was that an increase though? Oh, hang on a second. That's a decrease. Okay, remember this negative sign? Although I didn't include it in the final answer, it's telling me that it's a decrease. So I gotta remember that's a decrease. So I actually didn't exactly gain GPE. I kind of lost it, but never mind. Let me just write it down here as well. So this will be negative 1.93 from my previous answer times 10 to the negative 49. Wow, so small. Yellow. Okay. If you're still wondering why is there a minus sign, you look at this graph. This is the total potential energy that's changing. The scale is a bit off. So if I were to draw it to scale, your change or decrease in gravitational potential energy will be much smaller. So something like this, perhaps. Yeah, something like that. Whereas your change in electric potential energy will be much bigger like this. So This one will be higher lah, okay? This final point will be higher than down there. So you minus off to find what is the gain in potential energy. Okay, minus off the little GPE that was lost. Okay, so we continue our calculation. We'll find that kinetic energy is 3.03 times 10 to the negative 14 joules. If you're very happy and say, yes, I'm done, hold up, hold up. Look at the highlighted part on top. They want you to find it in MeV. So you got to do another conversion. You're like, okay, I will find my conversion. So we need to convert this to EVs. If you forgot how to do that, here's a good refresher. Divide by 1.6 times 10 to the 19. Looks familiar, right? Then you would have your unit in EV. What's this value? 0.19 times 10 to the 6 EV, which is about MeV. So yeah, problem solved. So that's 3 marks here. First one is you kind of got the idea of energy change. You knew to convert to EV and you actually did convert it properly. A reminder again, if you have EV and joules, if you want to convert from, let's say, joules to EV, okay, you will need to do something called multiplication and division to convert it back and forth. So here, next time you see a joule, they ask you to convert to EV, you divide by the constant E, which is 1.6 times 10 to the negative 19. If you have EVs, you want to convert to joule, you multiply by E. Please remember this when you're dealing with particles. Last part. The two nuclei may rebound for each other, we don't know. Suggest one effect that could happen if they have if the initial kinetic energy is greater than what you calculated. Oh, this is interesting. Imagine this as a collision. So let's say the current state is this. At first they start off pretty far, number one. And then they come really, really close. But they just about stop moving when they just about touch. So something like this lah. Okay, they stop moving when they touch because they have just enough kinetic energy to reach that distance. Okay, so I'll write a reminder here. All the kinetic energy, total kinetic energy, became all the potential energy, gravitational and all kinds of whatnots. Okay, just nice. But what if now you have a bigger total kinetic energy at the beginning? So maybe you have the potential energy, which is the same, but you might still have an extra kinetic energy at the end. Okay, because now this one is bigger. They come colliding towards each other at a faster speed. So they won't just stop moving when they touch. They might in fact slam into each other and go like pa-boom, collision. Something happens. Okay, so this one is when they both stop moving just nice when they touch. But now you start off with a bigger speed, so you go, I can't stop it, I still have energy. Pop, and they smack each other. So what could happen? This is just a 1 mark question. Well, if you remember particle physics, there are a few things that can happen. Number one, these guys, when they smash together big enough, they might split into subnuclear particles. So that's one possibility, okay? So the deuterium may split into subnuclear particles. This is what people do, what particle physicists do for a living. They smash particles together to see it explode and see what is inside the particles. So if you remember all those stuff, deuterium is, oh man, I should probably draw two, right? Deuterium is a proton and a neutron. Maybe the neutron and proton will separate out. Pew, pew, it all breaks apart. Maybe they might break into quarks, up, down, strange charm, top, bottom, depending on the energy. So they would break up into smaller components. Or you could say, maybe fusion would occur. Maybe they will join together if the energy is just right. You will learn more about this in the later chapter 26. Or you could just say fusion might occur. We don't know. Okay, fusion might occur. What is fusion, by the way? Fusion is when you have, let's say, before, you have a deuterium. So this is proton, neutron. Another proton, neutron. And they're coming together. If they hit each other at just the right energies, just the right conditions, they might join together to form a new particle. What has 2 protons and 2 neutrons? This looks very familiar. This is something that has 4 nuclear number and 2 protons. And you might have guessed it, it's a helium nucleus. So this one is a 2,1 hydrogen, also known as deuterium. Okay, so this one might join together become helium. I don't know. This is fusion. What happens in the sun when particles come together at just the right conditions? Also known as an alpha particle. It's all coming together now. Okay, so that's what fusion do. Okay, they just join together. But yeah, all these ideas, just choose one. You will get a B1 mark if you got it. Okay, let's move on. Whew, that's one question done. So this is how to use your equations for potential energies, how to think of them when you're doing that. Okay, next. Whoa, this one is a very tricky one about potential again. But let's see what we can do here in this question, MJ12 P42 Q4. What is the scenario? Please make sure you try this out before watching this, or at least try to read the question and attempt. Then you will realize, oh my goodness, I have no idea what's going on. It's okay. We're learning together. So you have a charged point mass and a proton. The proton travels to the mass and you have a graph. This graph comes from this particle going closer to the proton. Or if you want to think of it the other way, the proton is traveling towards the mass. Okay, that's easier to think about it. So this proton is going towards the mass. Closer and closer and closer. Okay, so what are we trying to do here? What's the question? Oh man. Use a figure to state and explain whether the mass is charged positive or negative. How we know? They didn't tell us all. No, we know the proton is positive. Yes, I know that. This is positive. But what's the other charge? I don't know. But maybe we can have a hint based on this graph. You see, as you bring the proton closer from a further distance, the electric potential decreases. Oh. Which means, if you can imagine the potential well, if you have a particle, positive particle, rolling into the well, getting deeper and deeper, eventually stuck there, and it's not going to come out by itself. What is that? Why is it doing that? This is what we call an attractive force. If it's a negative potential, means these two particles are getting attracted to each other. So probably at 0, this is a negative charge. That's why it rolled down. Remember we look at the volcanoes in the previous video? Okay, if it's a positive one, you can have a volcano up. If it's a negative, then your potential will be kind of going down. Negative volcano, you put a ball here, it will roll down to the middle. So that's how we can tell. Negative potential, attractive, which means our friend here is a negative charge. Let's draw a little line there. Okay, so we have to state and explain, right? We can't just say, oh, it's negative. 2 marks, man. What are we going to do? So we can say negative. That's kind of stating the answer, but you need to explain as well. So negative because you can talk about the sign of the change in potential. So because as R decreases, they're getting closer and closer. Potential, I'm going to save some space here. You should write out the whole thing, but I'm going to say potential energy decreases due to attraction. So attraction is linked to the negative one, which is why in gravitational fields we always put the negative there, because it's always attractive. So in electric field it's different, it depends. So the first mark comes from you saying that, oh, your observation as R decrease, PE decrease. So this is the first M1 mark. To get the final mark, then only you say negative due to attraction. Due to attraction. There we go. Okay, so make some notes about that if you have not. This one, this question, a lot of students died here when they did this, because you're like, what is going on? 2 marks for this. The gradient on a point on the graph is G. How convenient. Show that the electric field strength is EQ equals to G, where Q is a charge at this point. So you need to do some derivation. How do you get EQ equals G? The first hint is gradient. When you see gradients in the electric field question, the first thing you should think about is, I've seen that electric field is the negative potential gradient. So negative potential gradient, also known as the equation negative dV dr. dV dr is potential gradient. But we have a problem here. If you look at the graph, this is not a graph of V against R. This is a graph of U against R. U is a different thing. U is gravitational potential energy. But we only know that E is potential over R. No energy, just potential. Different things all. So how are we going to relate that? We have a problem here. We're stuck. How to relate U into our equation up here? Is there a way? Can you think of other equation that relates V and U? Think about it. Flip to your notes a little bit. How to relate V and U? There is this thing that relates potential and potential energy, and it's just a small difference. So U equals to Q times V. That's it. So U and V can be related by just charge, because potential energy takes into consideration the charge of that point. So let's write some rough working here before we write the answer there. So if you want to do that I want to somehow involve U into this equation. Let's rearrange it. How about U over Q equals to V? Then I sub in to the equation, so I get E equals to negative D. Wow, how to differentiate? Sub in V, I get U over Q. Okay, so Q is of the charge, that's kind of constant, so E equals to negative 1 over Q. I can take that out, and I leave du dr inside there. I think we got it. We have related successfully the gradient of this graph. So we know how steep this thing is. I draw a tangent here. The gradient with E. And if you rearrange this, you have QE, I guess you can ignore the negative sign, equals to gradient of this graph. Magic. I like this. So you need to stay calm. Whenever you see gradient, think about the E first and how you can sub in other equations to do that. Yeah, you have to know a bit of differentiation to do that here. But anyway, let's turn this whole working on the side into something we can write in the answer for 2 marks. Okay, so problem is, we know E is potential gradient, but our graph is potential energy gradient. Okay, so the first thing I can write is I will tell them, I know that the electric potential energy is the product of Q and V. I'm going to shortcut and just write this here. And since the electric field strength E is the potential gradient, do you have to write out the whole thing? Yeah, I would recommend it, because sometimes they accept equations, sometimes they don't. So I'm shortcutting here, but you should write out the whole thing. So since E is potential gradient, therefore the field strength E is 1 over Q times du dr. If you're curious where this working comes from, that's the previous part I wrote over there. Oops. Okay. So the negative is considered under the gradient lah. Okay. So what we're gonna do here is, I think this is it. If you can talk about this thing, then you should be good, because this is 2 marks. First thing comes from you knowing how U and V are related, because we have a graph of U. Second mark comes from you knowing how to relate gradients to quantities. So E is a potential gradient, but we need to find the potential energy gradient, which is this. This is what we call the potential energy gradient, because got du dr. Every time you see the du dr, dy dx gradient, think of gradient and slope. Okay, so if you can, also write out this last line in words. If you have space, please do. Okay, that's the part we can talk about that. By the way, if you're wondering, how do we get the EQ? Nah, you do the next step though. QE equals to gradient. Gradient is what? G. So from there, we can do the last step. EQ equals to G. Okay. Use the expression to determine the electric field strength 4 cm from the charge point mass. Okay, so the equation they give us even if you didn't solve it, EQ equals to G. Let's write out the whole thing lah. Gradient. So we need to find the gradient of the point here. Hey, I already draw nicely here. But at a certain point, right, at a distance 4 cm from the charge point mass. 4 cm from the point mass means here. That means I want to find the gradient. Let me rub off this thing. Gradient at this point. Right here. How to find gradient now? Normally, straight line, we can draw a triangle, but this is a curve. Whenever you see curves and you want to find gradient, you have to draw, first step, draw a tangent to the curve. I'm pretty satisfied with this one, so that will be my tangent. I encourage you to eyeball a little bit, see how you can roughly get a good tangent to the curve, where both sides have kind of almost the same area, kind of ish, because this curve is pretty symmetrical. So what we can do now is we do our good old paper 3, paper 5 stuff, find the gradient. So with this triangle, which is the gradient of the tangent, you can find points. So I'm gonna, just for convenience, write down my points here, which points I used. And there they are. One thing to be very careful is the units. Any prefixes. This is 10 to the negative 26, so I got to be very careful. When I write there negative 23, it means negative 23 times 10 to the negative 26. And up here, circle your prefix so you don't forget it's in centimeter. Convert to meter, please. Okay, so this is how you can do your gradient. You might draw something a little bit different. We'll see if you get a mark for that. Alright, back to calculations here. So gradient is, in case you forgot already, y2 minus y1 over x2 minus x1. So you plug in your points lah, okay? So E, we don't know. Are we trying to find that? Yeah, we're trying to find E. Natural field strength. Okay. So the charge is a proton. So proton will be positive 1e, which is 1.6 times 10 negative 19. Gradient, y2 minus y1. Let's go. So y2 minus negative y1, which is negative 23. But also, this is such an ugly thing. Okay, I'll leave it there so you can see. Times 10 to negative 26. Remember the prefix? This is like paper 5, guys. Come on. So 6.2 minus 1.6. times 10 to the negative 2. So I'll go through a little bit faster here. From here, you should get a gradient of, well, roughly 3.696 times 10 to the negative 24. Don't forget, on the left side, you still have 1.6 times 10 to the negative 19. So you can find your E. Divide it out, you should get kind of 2.31 times 10 to the negative 5. What's the unit? Volts per meter. Okay, meter, change everything to meter. So here I can find an answer. I guess I could write, my least SF is kind of 6. So I guess I will do 2 SF, more than, 1 more SF than my raw. So 2.3 times 10 negative 5. 4 marks to do this whole process. The first one comes if you attempt to draw a tangent on the line. Don't care how ugly it is, okay? So if you attempt something here, you got a B1 mark for trying to find the gradient. If you actually found the gradient, ooh, not bad. You might get 2 marks here. Now, the interesting thing is, there might be 2 possibilities. If your value is less than plus minus 0.3, you get 2 marks. If your value is a bit further away, so less than 0.6 plus minus, then you get 1 mark only. So if your value is a bit different, it's okay lah. Make sure it's not too different. So you gotta do some practice in finding gradients of graphs, curve graphs. Final answer, A1. Okay, done. This question is pretty tricky, huh? Gotta do some differentiation, some graph. I think it's a very good question that train you in different kinds of skills. So the last one, whew, this video is almost there. These questions take time to explain, guys. The last one is ON19, a very recent one. It's chosen because it is quite unusual. So first, what is meant by electric potential at a point? At this point, you should probably know how to memorize this thing because it's a free mark to write a definition. If you ever forget, just remember your AS, W equals to QV. So V equals to work done over Q. That's already 1 mark there. So work done per unit charge To do what? Don't say move a particle between 2 points. No. That's potential difference. We just want to talk about potential in this A2 chapter. So you want to think of a particle, you're moving from infinity all the way up to a certain point. So that's what you can say. So to bring a charge from infinity. Do you want to add to a point? No need lah. But if you feel like very free and the sentence is incomplete, sure, to a point. Infinitely far away to a point. 2 marks. 1 is from work done per unit charge. Final mark is from infinity to a point. Done. This looks really familiar though. In an alpha particle scattering experiment. Oh, isn't this from AS? The particle physics, the Rutherford experiment? Alpha particles are shot towards a thin film of gold. So it goes like bang, 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 bang. Shoots it to the right. And well, you can imagine a thin gold film. Thin gold film assumes that roughly there's one gold nucleus. One gold nucleus there, so either you hit it or not lah. So apparatus is in a vacuum. The gold nucleus are fixed point charges. Okay. So the alpha particles have an energy of 4.8 MeV. Very energetic. Calculate the initial kinetic energy in joules of the alpha particle. Is this a free mark? Okay, so we need to convert MeV to joules. Great. So remember again your conversion from EVs to joules. If you want to get from EV to joule, you multiply by E. If you want to go from joule to EV, you divide by E. So we are trying to get kinetic energy. We already have 4.8 mega, so 10 to the power of 6 EV. If you want to convert that to joules, you multiply by 1.6 times 10 to the negative 19, which is this one right here, lor. Okay, we're going to do that. So you should get a value of about 7.68 times 10, negative 13 joules. Final answer, I guess I could round off to 2 SF if I want to, because everything's minimum is 2 SF. So sure, okay, I'll do that. But I'll save my 7.68 for a later calculation, because it's just more accurate lah. Okay, 1 mark, final answer, correct lah. Okay, so what are we going to do with this now? Find the distance of closest approach to an alpha particle. Wow, closest approach. So imagine this alpha particle is getting really close. They get really close, but it may not hit the particle. Maybe not enough energy. So I assume it doesn't hit. My first assumption, it does not hit. Does not have enough energy to hit the particle. But it comes really close. It's kind of a little bit like the question we did earlier, where you had, what was it? This particle come very close. No, not this one. This one. Particle come very close. This one, they just touch. But now, it doesn't seem like they will touch, because they say the distance of closest approach. So maybe they will come like very close lah. Maybe, okay lah. This one is big size, small size. Maybe they come to here, roughly. Then they stop already. They reach a point where V equals to 0. They stop moving. Or EK is 0. So you need to write the energy conversion like in AS as well. What is loss? What is gain? So you have a loss in kinetic energy of both particles. Actually no, only one that's moving, alpha particle. So loss in kinetic energy. But what do you gain though? You have a gain in potential energy. Oh, both positive, oh. Right. This is positive 2E. Alpha particle is charged. Gold film is what charge? How do we know? Here, hint. When you see 79, that means it has 79 protons inside the nucleus, which means the charge is plus 79E. That's a very big positive charge compared to our tiny alpha particle. So one of these guys have 2E, and one of these guys over here have 79 big E's. Okay. So that will be a big gain in kind of electric potential energy. So E, I had to write there PE lah. Okay, sure. So what's the kinetic energy that was lost? The whole thing. In fact, we already calculated. So that was 7.68 times 10, negative 13. All gone. Because it stopped moving. Really close. And all being converted to potential energy. So Yeah lor, you can think of it this way. If you want to think about, Miss, where's the minus sign? Nah. Final final minus initial, right? Or something like that. Usually there are minus signs, but since we already know what is loss, what is gain, we don't need to worry too much about the sign. So how to find EPE? You need to remember electric potential energy is KQQ Q1 Q2 over R. So we write that down here. So this will be K is 1 over 4 pi epsilon. Go and find the E naught constant in your data formula sheet. Q1, Q2, both charges. One is positive, I should put positive here, positive 79E, the gold nucleus, and positive 2E for the alpha particle. Side note, E is 1.6 times 10 to the negative 19 coulomb. Okay. Divide by the separation distance. Oh, we don't know. That's what we're trying to find. Okay. How close can they get? Alright, let's see if you have enough energy to get close. So if you calculate everything properly, you should get about 4.736 times 10 to the negative 14. Not bad. It's not zero, means they don't touch, but they get real close. Almost there. So this is about 4.7, rounded off, times 10 to the negative 14. 4 marks for this. First one is, do you know this equation? Memorize, at least memorize if you can't understand it. Second mark is, did you know what is the charge of gold and alpha particle? Oh, throwback to AS, man. And the last one, wait, how many marks I did? 1, 2, oh, 3 more, 2 more. Oh, okay. If you wrote the whole equation, you sub in the correct values, you get another mark, and final answer, 1 mark. How many did you get? Check yourself. The final part is an estimation question. So now they ask you to use your answer to comment on the possible diameter of a gold nucleus. Huh? What do you mean possible diameter of a gold nucleus? Okay, so let's slow down a bit. Just now we already said that the closest, what's the closest distance? The closest the alpha particle can go to a gold nucleus is this 4.7 times 10 negative 14. So let me draw it out for you. Our calculations were based on the assumption that these two are point charges, right? One have a charge of plus 2e, the other one have a charge of plus 79e, was it? I think, 79e, correct. And this is the closest they can get. This is distance d. So what is a possible nucleus left? If you think about this way, the alpha particle can only go up to here. So maybe it's flying in from very far. It reaches here, then it's like, whoops, I can't go any further, and then it bounces back. Okay, that's the closest it can go. So you could say the limit, the no-go zone of this particle is kind of this big area. It cannot go any closer than that. And that's because it doesn't have enough kinetic energy to go closer lah. So the distance here, we have already measured that to be 4.7. Is it 4.7 times 10 negative 14? That is this distance right here. So you could say, okay, the gold nucleus could be anywhere smaller than that. Maybe it is this circle, or maybe it's even smaller. Maybe it's a dotted line itself. We don't know. It could be smaller as long as the nucleus is smaller than this dotted line, or equal or smaller than. So if you want to find the radius, the diameter of the nucleus, then here is 4.7, here is 4.7 times 10 negative 14. So this 4.7 is the maximum possible diameter of the gold nucleus. Cannot be bigger already, because after that you're gonna have collisions, okay? So what you can say is the possible diameter is roughly 2 times, I should not use D because these are diameter is roughly 2 of this distance D, which is roughly 9.4 times 10 negative 14. Okay, this is the maximum size that it can be to fulfill these conditions where the alpha cannot go closer than that. So your answer can be an estimate law. As long as it is smaller than 10 power 14, you should be fine. So what we usually can say is the diameter must be less than a scale of 10 to the power negative 14. Usually this is 1 times 10 to the power negative 14, and you should be good. The mass scheme says they allow times 10 negative 13, because if you round this off, this is kind of close to 1 times 10 to the power negative 13, because 10 times 10 negative 14 is that. But I would be more comfy just saying diameter must be smaller than 1 times 10 negative 14. Okay, so this one is just a B1 mark for guesstimation question. just to figure out, roughly guess what is the diameter there. Okay, so that is all for this whole section on point charges. Remember how to use your equations, how to think about charges, apply all these fields to it. But that's all for this example video. I will see you in the next theory video.